Okay, now once more, our central relationship is omega equals the square root of K over M, related as indicated here to the fact that the net force is linear restoring force, so the force F net equals negative Kx. K has a name, it's called the force constant. In SI units, it's measured in newtons per meter. In any case, it's measured in units of force divided by units of length. Omega is the angular frequency, measured in radians per second in the SI units. Could also be measured in degrees per second, revolutions per second, any measure of angular displacement per second, but in SI units we'll use radians per second. And M is the mass, and as we know, the SI unit for mass is a kilogram. Excuse me. Now we have a 400 gram mass, which is of course 4.4 kilograms, and it has an angular velocity of 40 cycles per minute. Now, just because I use omega doesn't mean I have to have radians per second here. I have to have radians per second if I want the units to articulate in the SI system. So I would want to express my 40 cycles per minute as in units of radians per second. Now, when we asked in class, okay, how would we proceed to do this? First thing somebody said was, well, a minute is 60 seconds. So I'm going to take that minute and write it as 60 seconds. Then somebody said, well, let's see, no, a cycle is all the way around a circle, so that's 2 pi radians. So I got two very good responses there, and that's true. So we then replace the cycle with 2 pi radians, and we just do the arithmetic, and we end up concluding that 40 cycles per minute is 4 pi over 3 radians per second. Of course, we can do that whole thing in one set of substitutions, substituting 2 pi radians for a cycle in 60 seconds per minute. We get 40 times 2 pi radians divided by the quantity 60 seconds. And the arithmetic is very simple. 40 times 2 is 60. 40 times 2 is 80. 80 divided by 60 is 8/6 or 4/3, and we have that pi, so we have 4/3 pi, and we have radians per second. Okay, so what we're asked, of course, is what's the force constant? Now, we have the mass and we have omega, so we can use this relationship to find K. Omega equals the square root of K over M, so K is M omega squared. Mass is 0.4 kilograms. Omega is 4/3 pi radians per second. So M omega squared is calculated here, and we end up with something approximately equal, fairly close, to 8 kilograms times radian squared over second squared. Now, the radian is a unit which, when multiplied by or divided by a meter, can give you a meter, because a radian of radius multiplied by, a meter of radius multiplied by a radian of angle gives you a radian of distance along an arc, and a radian of distance along an arc divided by a meter of radius, a meter of distance along the arc divided by a radian of angle gives you a meter of radius. So the radian can always disappear, in a sense, and give you a meter. And it can do other things, and I'm not going to get into all the technical details of it. I'm just going to say that, okay, kilogram times the radian squared per second squared can be represented as a kilogram per second squared. You can just kind of, the radian unit can, in a sense, sort of disappear when you don't need it in certain situations, okay? So this kilogram radian squared per second squared becomes a kilogram per second squared, and a kilogram per second squared, well, we're getting K here. What should the units of K be? They should be newtons per meter, but they're kilograms per second squared. Well, we can easily show that a newton divided by a meter, a newton is a kilogram meter per second squared. Dividing that by a meter, we're left with a kilogram per second squared. So the newton per meter is the same as a kilogram per second squared, and we have come up with the right units. So we've determined now that K is 8 newtons per meter, or approximately 8 newtons per meter, When a 400 gram mass or 0.4 kilogram mass undergoes simple harmonic motion with frequency 40 cycles per minute, which is of course the same as 4 pi over 3 radians per second. Now we actually suspended a mass from a rubber band. This mass is only 50 gram mass, and it oscillates several times per second if we allow it to oscillate. I add 50 grams and now we have a 100 gram mass. Notice that the rubber band got longer, and now we can have a little slower or a little less frequent oscillation, a lesser angular frequency, and now it's slowed down pretty reasonably. And we have now, we had 50 grams, we added 50 to get 100, this is 200. We can add another 100 to make it 300 grams, and we can even add a little more than that to make it 400 grams. And we can of course measure how much the rubber band stretches with each added increment and get an idea of what the force constant of that rubber band is. Now, the rubber band doesn't exactly follow an F net equals negative kx. Early in the semester we measured rubber bands and we did graphs, and we learned that that was the case. So now we're using that insight that we gained back in late August or early September about the way a rubber band stretches and how much tension and so forth it takes, and we're applying it to this simple harmonic motion. So what we saw was that 400 grams suspended from a certain rubber band gave us 15 complete cycles in 10 seconds. Okay, counting 1, 2, 3, 4, 5, and so forth. It's a little faster than that to get 15 cycles, excuse me, in 10 seconds. Okay, well, 15 cycles in 10 seconds is 15 times 2 pi radians divided by 10 seconds, which is 3 pi radians per second. So that omega, our angular frequency, is 3 pi radians per second for that oscillation. The mass is 0.4 kilograms, and that would imply a force constant of m omega squared, just the same kind of calculation we did here. Now we got 3 pi radians per second instead of 4/3 pi radians per second. And we had the 0.4 kilograms, and we got a force constant of 36 newtons per meter. So that's quite a bit more than the 8 newtons per meter that we have here. Okay, we estimated in class what we thought the force constant might be. Actually, I just gave an estimate. So it looks like about feels like about half a newton per centimeter. Half a newton per centimeter. Well, you have 100 centimeters in a meter. That's going to be 100 half newtons if you stretch it out a whole meter. Of course, you can't do that with a rubber band because it'll break. But if you did have something that stretched like that rubber band, but could stretch all the way out to a meter, maintaining the same force characteristics, it would be 50 newtons per meter. Okay, so what we got was not far off of what I kind of estimated by feel, but that was no particular skill on my part. That was just kind of dumb luck. Okay, so we could calculate the force constant of that rubber band to the extent that it is a force constant. As I say, it really isn't constant. And then by adding weights to this, we could confirm that that really is the force constant. So that's just an application of this basic principle applied to a real system in the lab.